In this video, we illustrate the Nernst equation by looking at a couple of numerical examples. The first one considers an aluminum manganese battery, which is built as follows. Suppose that you have the oxidation of manganese in the anode and the reduction, the oxidation of aluminum in the anode and the reduction of manganese in the cathode. Okay, so the balance reaction is going to be like this. And then 3 manganese solid. All right, we're trying to build a battery out of this redox pair, and we're going to build electrodes with concentrations that are not 1 molar, so we will not be working at the standard state. Instead, they're going to be 1.5 molar and then 0.5 molar. Okay, so here's the idea. This aluminum 3 plus will be 1.5 molar, and this manganese will be 0.50 molar. Right, so the idea would be how much voltage are you going to get out of this battery with these concentrations, not 1 molar, which would be the standard state. Well, that's what the Nernst equation allows you to calculate, right? The cell potential under any concentrations, including this, is going to be the cell potential at the standard state, and then a correction that depends on the concentrations of those species. Okay, where this only works for room temperature, and then here you have your logarithm of the reaction quotient. All right, so the first thing that we need to do is to calculate exactly what is the standard state cell potential. And for that, we simply have to figure out what are the cell potentials of the half cells. Okay, this is going to be simply the cathode minus the anode, and this will be the standard reduction potentials as they appear in tables. Okay, so then let's try to write those that redox pair a little bit in more detail to see which reaction is in the anode and which reaction is in the cathode. That is that this is an oxidation, so that is going to operate in the anode. Okay, the reaction will be 2 aluminum atoms to generate 2 aluminum 3 plus ions plus 6 electrons, and this is an oxidation, which means that it's in the anode. And then the other redox pair will be the reduction of manganese. So we have here manganese, 3 ions of manganese 2 plus 6 electrons to generate 3 atoms of manganese. Okay, so this is your reduction, which takes place in the cathode. All right, so we already have our electrodes, and then we can just look at the tables for the standard reduction potentials of each one of those pairs. And in those tables, you have that the pair aluminum 3 plus aluminum has a standard reduction potential of 1.66 volts, and the pair manganese 2 plus to manganese has a standard reduction potential of minus 1.18 volts. All right, so then our standard potential for the cell will be the cathode, which is minus 1.18 volts, minus the anode, which is minus 1.66 volts. Okay, this gives us a standard cell potential of 0.48 volts. Okay, so we already have this piece of the equation. The next piece that we need to figure out is what the reaction quotient is under the conditions provided by the statement. Okay, so let's write that in a little bit more detail. All right, so notice that the reaction quotient is simply going to be the activities of products to the power of the stoichiometric coefficients, or the activities of reagents to the power of the stoichiometric coefficients, right? So this is going to be equal to the activity of this aluminum 3 plus squared times the activity of solid manganese cubed over the activity of aluminum solid squared, and then the activity of your manganese 2 plus ions cubed. Okay, remember that the activities of solids are 1, so then this is going to be 1, that is going to be 1, and the activity of ions in solution is simply the molar concentration divided over the reference concentration, which is going to be 1 molar. Okay, so in this case, notice that is going to be simply the concentration of your aluminum 3 plus in solution squared over 1 molar squared divided by the concentration of manganese 2 plus cubed over 1 molar cubed. So if we plug in here the concentrations that we have for the problem, this reaction quotient is going to be equal to 1.50 squared divided over 0.50 cubed. Right, so now we have all of the ingredients except for one, which is N. And remember that N is the number of electrons transferred. Okay? I have erased here the half reactions that we had, but notice that we, as written, we actually had 6 electrons transferring between the 2 electrodes. All right, so then your final answer will be the cell potential is going to be equal to the potential of the cell at the standard state, which is 0.48 volts, and then minus 0.0591, which again, this only works if we're at room temperature, over 6, which is the number of electrons transferred, and the units of these are volts, logarithm of that cube. Okay? All right, and when you do this, this happens to be 0.47 volts. So what you conclude here, what you can conclude here is that this battery will be spontaneous. You will be able to obtain electrical work out of it. Okay, it actually turns out that the difference in concentrations between the ions and the standard states are not large enough to cause a significant deviation of the potential of the cell operating under those conditions and at the standard state where the concentrations will be 1 molar. Right, so in the next video we're going to see a second example in which we see how all this applies to something that is called a concentration cell.